This is the first of 3 videos in which we're going to look at solutions to the tutorial problems in the vectors notes for mechanisms and structures. In each of these 3 problems, we're asked to find the resultant equilibrium forces for the systems of vectors that have been shown in the diagram. So in this video, we're going to begin by looking at question 1. To get started in a question like this, the first thing we have to do is to replicate the diagram we've been given, but rather than draw in a sketch representing the approximate sizes and angles, we have to draw in an accurate scale diagram where the angles have been measured correctly with the protractor and the length are proportionate to a scale that we've devised for the particular system. So we're going to look at question 1 in this video. We can see the sizes of forces in the question are 5 newtons and 10 newtons. So it would seem quite sensible to use a scale of 1 newton is equal to 1 centimetre. And that's going to fit nicely on our page. It means that a force of 5 newtons should be a 5 centimetre line, and a force of 10 newtons should be a 10 centimetre line. So we can draw in these vectors now on our page. And while there's no requirement to do this in your own work, I'm going to use different colours to show the different vectors I'm working on to make the question a bit clearer as I'm going through. I have the benefit in the whiteboard that I can set my ruler to be at a particular angle, but you need to use your protractor and set the angle as we've shown in class. But here I have a line moving upwards at 30 degrees. In fact, what we'll do before we even begin is we'll just mark a little starting point for both our vectors. A little cross here, and that will be our starting point. So I'm going to line up a line pointing at 30 degrees, and I'm going to draw a 5 centimetre line acting in this direction to represent our first vector, and I've chosen red for this. So 5 centimetre line or thereabouts. We will lose a little bit of accuracy when we draw scale diagrams. It's not possible to be perfect, but we'll do our best to be as accurate as possible. And what I should also do is mark a little dotted line along the horizontal to show where we're measuring our angles from, and this will, a good bit of practice will help keep you right when you're doing this on paper. This is our horizontal line. What we're saying is this red vector here is measured at 30 degrees from that line, and the size of the vector is 5 newtons. Now we're going to draw in the 10 newton vector, so I'm going to do a very similar thing. I'm going to get an angle of 30 degrees downwards from our dotted line, to line the ruler up with the starting point here selected. Now use blue pen for this vector and draw a 10 centimetre line. A 10 centimetre line, and straight away you can see that although the angles as intended point the same amount angled up and angled down from the dotted line, unlike the diagram I've been given in the question, they're not the same size and we can't treat them as such. The blue vector is twice as long as the red vector, and that has to be reflected in the work that we do here. The next step is to make a copy of each vector slid along to the end of the other one. So what I mean by this is we're going to take our ruler and we can go back to the red vector first of all, set our line to 30 degrees. Again, we'd measure this using a protractor and making sure our line is completely parallel to the first one we drew, line it up from the end of the other vector and draw another line of 5 centimetres, so completely the same line in the same direction, just over here. So 1, 2. And I can draw a little arrow at the end of this one as well to show the direction it's going in. And to complete our shape in this case is what's called a parallelogram. We'll draw in the final side, which is the 10 Newton blue vector pointing down the way. And it should, if we draw this correctly, line up with the two ends of the red vectors. And it does, which is exactly what we wanted. So what we've done so far is we've drawn in our two vectors to a scaled size, so that a 10 Newton vector is twice as long as a 5 Newton vector. We've drawn in the angles accurately. And what we're aiming to do now is to find the resultant vector. The resultant vector is what's the combined effect of these two vectors. So we can see from our diagram, they're both pointing towards the right-hand side, and one's pointing up the way and one's pointing down the way. So we can expect they're going to be pointing to the right. We'll see that in a second. And maybe our instinct is to be pointing a bit more down than up, because there's a 10 Newton one pulling down and a 5 Newton one pulling up. And that's exactly what we see. How we find out this overall effect is by taking our ruler, lining it up with our starting point. So we adjust it around until we find our starting point here, and drawing a line from our starting point to the point where our vectors meet at the opposite corner. So this is our angle here. Now, again, we might not be completely precise with this, but we want to get as good an effort as possible. So I'm going to draw a line across the screen here, starting at this point. And so this is our resultant, because it is the result of following the red line then the blue line, or the blue line then the red line. Taking those two vectors together would give us this overall effect of this green vector. So to finish saying something about the resultant, here's what we have to say. First of all, we have to measure the size of it. So you'll be able to do it much more accurately in a piece of paper than I can on screen here, but counting along these boxes, it's slightly over 13, so I might say about 13.2, maybe 13.2 centimeters. So our resultant, I'll say this here. And of course, 1 centimeter equals 1 Newton. So that means our resultant force is 13.2 Newtons. We also have to say what direction it's going in. So usually what we would do is we'd measure this angle here, and I'll mark it in green to show it's for the resultant. We measure this angle here, the angle between a horizontal line, or sometimes a vertical, to what's most convenient, but we give some indication of the direction it's pointing in. And if I use my ruler here, well, I don't need to use a protractor because I can see that's 11 degrees from the ruler. And so I can say that the direction, 13.2 is the magnitude, and I should really write that here. The magnitude just means the size. Magnitude 13.2 Newtons, direction is 11 degrees, and we'd write something like below positive direction of the horizontal. It just means below a line pointing to the right. Or for short, you could draw something that looked a bit like this. Also dotted line with a line below it. Just to say, I mean, if we mark it clearly in our diagram, then that's all okay. What we want to make sure that we've given both a direction for our resultant and a size for it as well. The last part of the question, you'll see what we're asked to do here. We're asked to find the equilibrium force as well. Well, the equilibrium force we find in a very straightforward manner. We take the ruler, we line it up along our resultant, and then in the opposite direction, so Our resultant was going down and to the right. We're going to go up and to the left. We draw a line of the same length in the opposite direction, because this is the force we would have to add to this system to make sure there was no overall effect. So if I draw a line, I'll use orange this time, 2, 4, 6, 8. 2, 4, 6, 8, 10, 12, 13 and a little bit. I can draw a little arrow showing the direction of our equilibrium, and of course this will be going up the way at 11 degrees here. So for question 1, that's how we find a resultant, the green line, which would be the effect of the two forces added together, and how we find our equilibrium, that's the orange line, which would be the force required to make sure there was no overall force in the system. And of course, we can say this too would be 13.2 newtons. It's just the exact opposite force to the resultant.